Yeah, hello, am I audible? Okay, cool. So, yeah, hi, good afternoon everyone. My name is Gokulvanan, right? You can call me Gokul for short. So, in fact, Govin was talking about, the fulfillment systems in Flipkart. I've been working with, systems which come before that, which are involved in order capture and, order management, and we trigger the fulfillment process. So this talk, scaling write-heavy OLTP systems with strong data guarantees, is largely a work both by me and my colleague Pradeep S. We're both architects at Flipkart who work with these systems. So this talk is about our journey, actually, in terms of how we went about scaling the order capture and order management systems in Flipkart. So the way we would like to go about this presentation is, I'll first introduce you to what I mean by order capture and order management systems, right? Then I will focus on the problem we faced, in particular with scaling the systems and with respect to data stores. Hbase turned out to be our logical choice. I'll get into the why and how of that. And Hbase wasn't really a direct fit for our needs. We had to customize Hbase. So in fact, the second half of the talk would go technically deeper into those customizations we made, right, in order to, and the benefits we reaped out of it. So the first system I want to introduce you is an order capture system card. So in fact, this is where order capture starts in Flipkart. If you've been shopping at Flipkart, right, you'll be looking at products. You would see a button there which says add to cart. The minute you click, this is the screen you'll be looking at. And essentially, this is nothing but a digital manifestation of your shopping basket, right? When you're in a retail shop and you got a shopping basket. The type of store that is required to power such an experience has to be a CP store. I'm saying CP from consistent in case of a partition. The reason being that you don't really want a customer to add an item to cart and then look at the cart again to see it's not there. And the access pattern, for every customer there's a cart. So customer's account ID is the primary key, right? And these are, again, the interesting thing about the access pattern over here, it's more of a write and read heavy access pattern. What I mean by that is you don't see people coming onto flipkart.com and clicking on the cart button and just seeing the cart. Usually it's when you add some items to cart, you really want to look at it. You probably want to change your PIN code or you want to change the quantity, right? That also brings to the next interesting part, that the reads are hot reads. You're not really reading something that is very stale. The read-write ratio for this system is like 2:1. We get about cumulative QPS of 100K, and the data footprint's around 600 gigabytes. The second system I would like to talk about is checkout. So from cart, you click on place order, or from the product page, you click on buy now, right? This is the screen that you get redirected to. And again, the type of store that is required to power such an experience is a CP store, right? The access pattern is largely very similar to cart. It's again key value, where key happens to be your checkout session ID. And this is again very similar to cart. It's a write and a read heavy. No one's just going to read their checkout session. You're going to be working on your checkout. You're going to be filling in your address. You're going to be probably adding something else to your basket. You might get recommended for some other item that goes well with this. So it's a write and a read heavy store. The read-write ratio is around 5:3. And the cumulative throughput we receive here is around 70K requests per second, and the data footprint is around 500 gigabytes. The last system I wanted introduce you to is the order management system. So once you place an order, this is a system that manages your order. The screenshot you see here is your My Order screen, right? When you log on to Flipkart, you open up your account, you see all your orders. Now, even when you make a purchase, the first screen you see after you purchase, which is saying your order is confirmed, that's again from this system. So largely, the type of store which powers such an experience has to be a CP store. We cannot afford to be inconsistent in the order representation to a customer. The access pattern again here is key value, where key becomes the primary access pattern usually is based on your order ID. Give me the entire order block given an order ID. Minor deviation from what I spoke about earlier is that there are requirements for index reads. In fact, the screenshot I've shown you is where, given a customer's account, give me all his orders, right? And another deviation here is reads are much heavier than writes, right? You would probably just come check what's happening with your order. It's not that you're going to mutate your order every second. And there are random reads. So the read-write ratio of this system is like 10:1. The cumulative throughput we receive is around 120K requests per second. And the data size footprints around 2 terabytes. Again, all the data sizes I've been putting over here are without replication. So usually we run this with replication. So you can multiply them to 3 to really talk about the data footprint on the disks, right? And when you have data with such large volume, we usually don't put it on a single store. We usually tire the data store. There is, although I said there's random reads, there's always a temperature-based access pattern to these data. To give you an example, orders which are less than 6 months tend to be accessed more often. In fact, around 99% of the requests that come in are for orders which are less than 6 months. So we could leverage that in order to solve for performance. So when we started this journey, this is where we were. The system you see on the board here, cart, checkout, order management, payments. So largely these systems encompass the order capture and order management experience in Flipkart. And when we started our journey, we had, we have a nice service-oriented architecture. In fact, we have our own private cloud, and we leverage a lot of open source technologies. So we had each of these systems which were on their very respective data stores. Cart was using MongoDB, checkout was on Redis, payments was using MySQL, and OMS was using a combination of OLTP and Hbase because we had tired our data. So you can see all this, and you see there's a good separation of concern. What was our problem, right? And what were the challenges when it came to scaling? So largely, business required us to scale. And at Flipkart, the amount of traffic we were getting was growing by 10x on a year-on-year basis. And when it came to flash sales, it was a different ballgame. We used to get 1,000 times the traffic of what we get during a regular day. And the fundamental problem was fragmentation. We had to scale and tune each of these data stores that we were maintaining, right? So I've just listed down a few. This is not really to say one database is better than the other. So for example, in Hbase, which is a thick stack, we used to run multiple tables. We would run into hot spotting. So one particular table's region being co-hosted along with another table's region will result in hot spotting. Also, if you're tuning your Hbase based on an access pattern for a particular table, and another table has a different access pattern, you're going to run into troubles. With VoltDB, there was a concept of K-safety group. What that implies is you have a bunch of nodes, and let's say if your K-safety is 3, you got 3 nodes, and all your master partitions are distributed across it. And the funny thing about it was, if you take a node down for maintenance and you bring it back up, the master partitions no longer redistribute. Now they're just skewed up with the 2 nodes. And if 2 nodes go down for maintenance, all your master partitions are going to sit on just a single node, potentially becoming a bottleneck. With MongoDB, what I can recall is one of our NFR testing, we faced high number of context switches, which was the symptom for the tail latency problem. And just by looking at the documentation on the web, we weren't really able to tune and fix our problem at that point in time. The point I'm trying to make here is data stores, the open source data stores we used, could not be a drop-in solution to our scale needs. We could not just choose a database based on our access pattern and expect it to work with the kind of scale requirements that were coming in. The second problem we had was we had different solve for common needs. So as a data store platform, these are certain characteristics that we wanted, which were common across our systems. BCP-DR, right? Backward continuity plan. Either you go with full snapshots or incremental snapshots, or you're having a replication pipeline to move your data to a hot standby. Now, this had to have different solves. If you had to go with MySQL, you need a bin log replication with Tungsten. If you want to go with Redis, there's another external patch that you need to put in. And not all of them were very straightforward. If you wanted reliable BCP-DR, you had to invest some effort onto it. Change propagation. So all our systems in the user path, right, involved in order capture, followed a pattern of Lamdba architecture, right? And change propagation, what we mean by that is reliable, lossless data transfer, right, when we have an atomic transaction. And again, building this for each of the stores I had mentioned was a task. Tired data storage, the ability to partition your data based on its temperature of access, hot and cold. So the point I'm trying to make here is there was a definite need for consolidation, all right? Lack of consolidation was a big operational overhead for us in trying to maintain and meet our scale goals. So when we decided we wanted to consolidate, we went and we started jotting down what are the bare requirements and what were the acceptable trade-offs. So we needed high availability and strong data guarantees. But we are more towards the CP segment, so we could have a minor data availability loss if we had a cluster-wide disaster. We primarily had the requirement of key value lookup, all right? And yes, like there was a certain use case when we needed even index support. But the trade-off that was all right was we didn't need something as extensive as a B-tree index. We are all right with a simple lookup-based index. We needed lossless near real-time change propagation, right? At least once guarantee is all that we needed, because exactly once is another hard problem to work with. We needed predictable performance and horizontal scalability, right? So as scale requirement kept changing year on year, we wanted to be able to horizontally scale our systems. Latency under 100 ms was acceptable. We weren't very stringent for the P99, right? For it to be under 10 or 50 milliseconds. So with these requirements and these trade-offs which I just called out, to us Hbase seemed like a logical fit. And why? Well, Hbase was a horizontally scalable CP store. It offered strong data guarantees. It had an LSM engine with tunable levers for write and read heavy loads. And moreover, it was tried and tested in Flipkart. Catalog team had been using it for 3+ years. Us at order management had been using it as a cold store, although we were using the 0.94 version of Hbase. So in fact, we had deeper expertise on Hbase as well, which kind of also pushed our choice towards it. So let me try and justify what I meant by horizontally scalable. So, and also introduce Hbase to the larger audience here if you're not aware of it. So largely a Hbase is a thick stack. It comprises of a bunch of components. I've kind of color-coded Hbase and HDFS. So what HDFS is nothing but a distributed file system which distributes your data. So Hbase comprises of HMaster and regionserver that you see in green. And HDFS is primarily name node and data node. Journal node is a bunch of processes which run a version of Paxos to ensure you have a hot standby up and running in your name node. And Zookeeper is a coordinator between Hbase, regionserver, and the clients which talk to it. So largely when you use Hbase, the way you use it is you create tables. Like in this diagram, there are two tables. One which is the circles which are coated red in color, the other which is the one in purple. And when you create a table, you're going to basically partition the data in this table in the form of what's called regions, right? So the circle dots you see on the green boxes are nothing but regions. And each of these regions are an in-memory representation of the data, right? And the data in its file format is actually stored in HDFS. So if you really see, Hbase uses HDFS to manage data replication. So for example, if you look at the first server box, you can see region 1, and it's co-hosted data node holding a copy of it. And you can also see a copy of it sitting in the other data nodes, right? That totally 4 purple dots over there. So largely, when you get a lot of traffic on a particular region, you can always choose to add more boxes and have your regions, broken down further and redistributed across your boxes. This lets you scale horizontally. And I did mention Hbase had an LSM engine with tunable levers for read and write performance. So what I really meant by that, let me try to illustrate that by explaining you how LSM engine allows you that. So the way LSM engine works is it's in fact built for write heavy loads, right? So when you get a high throughput write request, you actually write to a sorted in-memory data structure that's called memstore in a Hbase context. And you write into an append-only log format, which is again called a val file in Hbase context. So because of this, your writes are really fast, right? You're writing to a sorted in-memory structure, and you're writing to a disk, which is just an append-only operation. When it comes to read, right, it's a little more different. So in fact, as you keep on writing, your memstores are going to grow, and they're going to flush to the disk in the form of H files. And as they flush to the disk, each of these files are again a sorted data structure, so they have a start and a stop key, right? And whenever you need to read, if your reads are hot reads, again, if you remember the systems I introduced you, right? I mentioned there were a few access patterns which are hot reads. So if you have hot reads, there's a good chance you'll be getting the data right from the memstore. But if your reads are not that hot and memstores flush the data into disk, you have to hit the disk and you got to find out which of these H files contain your record based on the start and stop, right? And obviously there are inner implementations like Bloom filters to make this faster. But largely, this is a disk hit, and that affects your read performance. So that's where periodic compaction comes into play, whose sole purpose is to ensure you collate your files, reduce them, merge them together, so that the reads don't really have a lot of disk lookup to happen. So this is how a LSM engine works, and what you get to tune is you get to control the memstore size, you get to control the compaction interval, and this way you get to work with read and write heavy access patterns. So what was our challenges? Like I mentioned, Hbase wasn't a direct fit for our needs, right? So one of the problems we had was Hbase is a very thick stack. It's unlike RocksDB where you can just put it and it's very thin. This was a very thick stack. It, like you saw the slide before, it has a zookeeper, it's got hmaster, it's got region servers. So largely we couldn't really, or it was a big operational overhead for us to set up a Hbase for every single table, right? So we started setting up a single cluster and reusing it for multiple tables. But doing so gave us a problem of resource isolation. So one table region could hotspot and affect the other. So what we really wanted was multi-tenancy in Hbase. The second challenge we had was there wasn't really a inbuilt support for change propagation in Hbase. And largely this was extensible from Hbase 1.2.4 by adding a custom replication handler. The last customization we did was related to index support. Hbase is a simple key value store. So we realized that our index requirements were very simple, that we could actually pull it off with dual writes and reads, and yet have a trick in making sure we have strong consistency. Read your own writes consistency, if I may. And I'll get into that a little more in detail. So the next set of slides from here is actually going to explain each of these customizations in detail, right? Mostly through pictures, so that I hope rest of you can follow as well. So the first customization we did was multi-tenancy in Hbase. And when we started off with this problem, we spoke to a bunch of folks who were Hbase committers, and we figured out there was already a patch sitting on the master version of Hbase code called regionserver group-based assignment. This basically brought a notion of having a bunch of region servers tagged with a name that's called rsgroup, right? And you could then create tables again tagged with this particular rsgroup name and ensure the regions created for this table is going to sit only on those region servers. And this is exactly what we wanted, right? So largely our work was understanding this and backporting this to a stable release of Hbase, which was 1.2.4 at the time we started doing this. So let me try and explain, how rsgroup works. And to do that, let me first focus on Hbase, right? And I've kind of color-coded these slides if it helps when we go further. So largely the servers are the gray boxes here. You can see certain processes are co-hosted. The greens are Hbase related process. HDFS processes are color-coded in amber, zookeeper is in blue, and the journal process in yellow. But largely what I want you to understand from the slide is when clients or the apps which are talking to Hbase are not really going to be talking to the hmaster or the name node. They're going to basically first just talk to the zookeeper, figure out where their regions are located in the region servers, and thereafter they talk directly to the region servers, right? So in other words, the way Hbase works is that clients talk directly to region servers. And if you can achieve that the regions of a specific table do not really co-locate with the regions of another table, you in a way ensure that the traffic for one table does not hit the other boxes. So let me say what happens when you actually use a normal Hbase cluster. So this is an example of a simple Hbase cluster in which there are two tables, red and purple. Pink and purple. And let's, for the sake of assumption, say that the red table happens to be checkout and the other one happens to be cart. And if we put them and all their regions are, spread out and interspersed in all the region servers. So now what's going to happen is if checkout is under very high load, it's going to affect even cart's performance. Let's take the first box which contains both the pink and the purple region, right? So if one region is, eating up all the resources which is meant for another region. What we want to achieve with rsgroup is essentially tag a bunch of boxes and say these are for checkout. Tag another bunch of boxes, say these are for cart, and then ensure when we create tables, they sit and are assigned only to those boxes. So how did we go about this? Well, to understand that, you need to know how Hbase assignment works, right? So largely I'm introducing three components on this slide. The load balancer, which sits in the hmaster, is nothing but a component which provides you a region placement plan. So it runs the balancing algorithm and provides you where each regions need to sit. Assignment manager is another component who executes on this region placement plan and is involved in ensuring it places the regions in the right boxes. And in doing so, it also updates the meta table, which sits in the meta region that's been shown over here in yellow. So what we've done essentially is that when we notice that when you create a table, right, the default implementation of this load balancer will distribute all the regions of this table equally across the region servers based on the load averages on each of these boxes. So for example, here I'm trying to create a table with 5 regions, and you can see it's spread out, and it's using all the 5 regions because none of the regions have any load, so it wants to spread out the load. What we have done is we've introduced 2 customizations. We've written our version of the load balancer called rsgroup load balancer, and we basically introduced a new meta table called rsgroup meta. So the way this now works is that when you add boxes, right, to Hbase cluster, you get to go and configure which of the RS groups or which of the servers are linked to a particular RS group. And then you get to also configure when you're creating a table to what RS group does it fall into. Now, the RS group load balancer, reads this information from RS group meta table and ensures that when it needs to do its balancing operation, it will ensure that the regions are assigned only for the region servers which have the same tag name as the table. Right? So largely, again, when the table gets created, the region servers sit within these boxes. So now when clients are going to be talking to a service, or let's say checkout, if this was checkout table, the checkout client is largely going to be talking only to 3 of these region servers and not the rest. That way we've got CPU and network isolated for these boxes from the rest. I just said CPU and network and not really disk because largely we haven't really solved for the data isolation problem. The data sitting on disks is managed by HDFS, which has absolutely no notion about region server group and all the customizations we did on the Hbase stack. So if you can see this diagram, it's illustrating the problem, right? We have clearly the purple table and the red table sitting on independent region servers, but you can see that data files and their replicas are interspersed. And how did we go about fixing that? Well, thankfully, Hadoop 2.7.3 already had introduced or exposed an API called as favored node balancing, right? So the concept of favored node balancing is simple. You have an API, when you talk to the right output stream to HDFS, you can specify the nodes in which you want the replicas to be present. So that way, when Hbase is creating a region or opening a region, right, that's when you're actually creating an output stream to your HDFS file system. And by having this knowledge of RS group and the regions where we want the boundaries to be set, the region servers, we were able to inform HDFS where we wanted the replica files to sit. So that kind of nailed the problem of ensuring we have isolation from CPU, network, and disk, right, for each of these specific tenants which get onboarded into this particular multi-tenant cluster. The second customization we were working on was to solve for change propagation. What I mean by change propagation is essentially transactional export. When there's a write that happens to an OLTP store, the requirement is we don't have any loss in the data that is written, and we have it exported out within a boundary of time. And largely we needed this because a lot of the systems in order capture and order management were built on this pattern of Lambda architecture. And we used to have this export, like for example, in case of OMS, it would go to Elasticsearch to power our search cases, which were eventually consistent. In case of checkout, it used to go to a Kafka cluster, which would pipe into a lot of data streams. Archival, auditing, they were all built on this pipeline, right? So the way we went about this is we first actually looked at what we could leverage, which was already existing, but figured out from the Hbase 1.2.4 versions, all we had to do was plug in a custom replication handler. So the 3 components I'm introducing you in this slide, right? One is the replication source. This is nothing but a daemon that runs inside your region server whose sole purpose is to tail your val log files, like your bin log file of MySQL, right? And replication sync, again, is a component sitting inside your region server, which is like an interface, right? And it has multiple implementations. There can be an implementation, the given implementation from Hbase are like for inter-cluster and intra. If any one of you set up a Hbase cluster and you set up replication, what you're essentially instantiating is the intercluster replication handler. And replication sync manager, which sits in the master, is nothing but your admin interface, right? So when you actually go to your Hbase master cluster, which you see in this diagram over here, and you try to add a peer, what you're essentially doing is you're instantiating a version of intercluster replication and passing it information about the zookeeper of your slave cluster so that it's a master-driven push replication that's happening. So what we've done is essentially we've customized the implementation of replication sync so that it is seamless, right? You could just add another peer and you can co-host a jar which we have built, which lets you now just sync your outbound stream into whatever channels you need. And largely we've written it for Kafka. So the best part of customization 1 and 2 was that multi-tenancy along with change propagation was a big gain for us. So the diagram I've kind of illustrated is you can assume the yellow ones is checkout and the pink ones are order management system. So largely we are having 2 tenants sitting on a single Hbase cluster and configured to different change propagation endpoints, right? Checkout pushing to Kafka, which powers a whole lot of other cases. OMS pushing it to Elasticsearch. The third customization we had worked on was to provide simple index support, right? So our use cases of index wasn't really profound. So what do I mean by simple index? So in fact, we've discussed about it to see if we could get rid of index support requirements. But largely we broke down the use case and found out the kind of requirement we had was very specific. One type of index that we classified was immutable index. What do I mean by that? Let me try and illustrate that with an example. So an immutable index is nothing but an index where, let's say you have an order, right? And you're making a transaction. You're paying money in order to purchase an order. So there's a transaction ID which is mapped to an order ID. There's no case of this particular transaction ID to be mapped to any other order. So it's immutable. That's exactly what I mean by immutable. Another type of index which we required was append only, right? So again, the requirement here, to explain it from an example standpoint, is let's say you're given an account ID of a customer, and the customer is making purchases and buying a lot of orders. You just want to append the new orders that are being purchased. There's no question of removal. In other words, an order linked to an account is never going to be linked to another account. But yes, it's mutable because you're appending, but there's no question of deletion, right? So largely, since these were the only 2 patterns of our index use cases, we realized that index could be, just be represented as lookup keys. And we could build this as an abstraction over the client or over the Hbase coprocessors. So what we essentially do is we do dual writes. And yes, when you do dual writes, you have a problem of distributed transaction. And the way we go about it is we use a trick of multi-version concurrency control, similar to what you have in Apache Tephra. So the way we go about it is we make sure we write the index first, right? And then we write the data. And what can go wrong in case of a distributed transaction failure is that you could have a stale index. And since we have both index and the data versioned, we would know that when you read a stale index which points to an order, and you then go look at the data for the order, you realize that the versions mismatch and the index is stale, right? And as a result, you can read repair if you would want to, or you could have a background process which cleans up your stale indexes. So largely, the trade-off in this approach is that you're going to have dual writes. You're going to have additional call for every index read and index write. And you're going to have false positive indexes. What I mean by that is stale indexes which you need to clean. But with these 2 trade-offs, we still were able to meet our scale goals, and it kept our design simple in terms of keeping our system ready for higher write-heavy loads. So what were the benefits? I've taken you through the problem we had and why we went with consolidation. And even when we did go with consolidation, I've gone a little deeper in trying to explain what we didn't find as a natural fit and required us to customize and go further. So the benefits we reaped out of it is largely now we have a single Hbase cluster which is multi-tenant, and we're able to predictably scale as our business requirements grow for each of these systems. There's very less operational overhead compared to what we had before. There is some resource savings because this is a thick stack and we were not really using the zookeeper and the name node components to its full potential. Having said that, the common components are the sequential elements to our design, so there is a limit to horizontal scalability, but we are way within the bounds of 100 nodes, and these have been proven to go for around 1,000 nodes. So we have a single cluster that gets about 500,000 QPS at the cluster level, and it's simpler to onboard new tenants. And in fact, we are in production with this now for the systems I mentioned, and a couple of learnings that we've had is it helps us now to even focus on a specific problem. So largely, the system resource that we tend to bottleneck on when we get very high QPS is the disk throughput, right? So the chart I'm showing here is from Gokulvanan, which talks about the write QPS, the increase in compaction throughput, which results, again, there's an increase in memstore flush because of the write QPS, and you can see the tail latency is going up to 75 milliseconds. And largely, the prime suspect and what you can see is the disk throughput, right? You run SAR minus T, you see you're 100% saturated. And in fact, what we've been doing now and what we're working on is trying to look at ways to reduce this saturation. A lot of work has been done on an LSM engine on the same lines in terms of compaction improvement, because compaction is one of the other threads which is actually doing a lot of reads and writes to disks. So a lot of work on this has been done for RocksDB, which are more or less portable to Hbase. We're also trying to look at new patches and ideas which are involved, and we have a lot of RAM. So we're trying to see if we could compact the in-memory data structure memstore rather than having it flush to disk all the time, and work on the disk for compaction. So memstore flush throttle and compaction throttle are things we're looking at. We still haven't got absolute data isolation. So whatever I had explained to you was on the files which were created by memstore flush. So we're working out to improve data isolation for the val file that gets created. And yes, there are certain edge cases. For example, when a node crashes or when you have a network partition that there isn't an ordering guarantee, you will definitely get your data, but we don't have ordering guarantee in change propagation. So that's another thing we solved for it now already by ensuring we have a buffer which is maintained at the consumption to ensure ordering, but we're actually working on the patch which is existing in master to improve ordering guarantees in change propagation. So yeah, with that actually I'm done, and you can open up for Q&A. Thank you.
Hi. Would like to understand, when you add more data nodes, HDFS has the concept of rebalancing, right? But now when you tie the blocks with distinct nodes, how does rebalancing happen there?
So when you add, the question is, when you usually in HDFS, when you add data nodes, there's a concept of rebalancing which is done by the name node. So yes, now that we've prevented name node from taking care of balancing for the nodes we've pinned, a lot of this is now managed by Hbase. So when you do add data nodes, you're also adding region servers, which are co-hosted. And regions are going to relocate. And every time region relocation happens, it's through the balancer. Balancer decides how to rebalance the regions across the nodes that are added. And rebalancing, the process of rebalancing is opening and closing a region, right? So when you do that, opening of a region creates a new file output stream, which starts writing to the disk again. And that is again redistributed across the data nodes given in the RS group. So in short, we are moving it to a single source, which is Hbase rather than HDFS.
Okay, and maybe two more, but very quick.
Sure.
So you were telling about append-only index, right? Where you had an account ID and order IDs kept on getting appended.
Correct.
Right, but sometimes an order can be cancelled, right? So it can be also be, a deletion is also possible, right?
So an order cancelled is still to be shown to a customer. So when customer cancels an order, if you really think about it, at least from our use case standpoint here, every order customer placed, whatever action he does on it, because an order comprises of money and product serviceability that we are given to the customer. And if he were to cancel it, he still needs to see it and see its refund status. So there's no question of deletion that at least occurs in this use case.
So it is updation then, basically?
It is updation to the order entity, but the index remains append only in this particular scenario. Yeah.
Okay, and there was one more slide which talked about a stale entry where I think there was a transaction.
Correct. So you're talking about this.
Yeah, right. Isn't the data stale rather than the transaction?
So yeah, so let me try and explain this a little more simpler. So when we are doing a distributed transaction, the problem is one of the transactions can fail. So what we are ensuring is we sequentialize it. We ensure we create the index first and then the data.
Right.
So the only thing that can go wrong when you sequentialize now is that the second transaction, which is writing the data, can fail.
Right.
So which means, in the example we are talking about, right, like account ID and order, you could end up creating an account ID pointing to an order, but you would not have the order, right? And when you're trying to get now this order information for the account, you realize that this particular index is stale.
Right, but actually the problem should have been fixed in the order side, right? The data order should have been written now, right?
Ideally, the data order should have been written, and that would happen through retries from the source system.
Okay.
But I'm looking at, okay, maybe this wasn't the right example, but from a systemic standpoint, let's say there was a write that happened which wanted to create index and an order, and it turned out the write operation failed and never concluded. Now, if anyone were to read at this particular point, to give you an example, there's an update that came, right, from our, let's say, fulfillment systems, and we are creating an index based on that update to our order. And this update failed because of a distributed transaction failure. So essentially, this has to be replayed now, right? And if this is not replayed at that particular juncture, if there's any reads that are happening, we shouldn't be supporting such an index lookup. So that's what this guarantees, right? The source system takes care of replay.
Thank you.
Sure.
Next question.
Hi. So when we are talking about reads,
Okay, yeah, sorry.
So when we are talking about reads, are these reads just index-based, or are we talking about searching as well?
I'm talking about only gets, no searches. So these are just index gets. So we don't, at least, we mapped our systems in a way where we give full consistency for a very few access patterns, which are on primary keys, and over and above these set of index lookups. Any sort of search is usually eventually consistent, and we do it through Elasticsearch. That was the pipeline, in change propagation that we've done. So largely we've mapped our business needs that way.
So when we are talking about all this stuff, so when Flipkart lists all the items, or someone comes and searches for a particular product, this doesn't come in picture.
No, so this is, okay, when you're talking about search, that's a different team that is at Flipkart solving for discovery. And in fact, there's a lot that goes into it rather than full text searching. There are a lot of elements into understanding the customer and recommending the right things for it. This is more from only the order capture and order management. So you've decided what you want to buy, and we want to ensure you can, we have systems which will ensure that you don't run into problems when you place the order into our system. So we're starting from cart, checkout. Those are the systems we are talking about here. Yeah.
So you mentioned in this slide itself, handling distributed transaction using MVCC. So are you using logical timestamps or physical timestamp for MVCC?
Actually, we're not using timestamps. I just used that for an illustration. What we do is that we imbibe the index in the order entity. So for example, if you're writing item ID as an index or transaction ID as an index to an order, right? So the row key in the index table would be a transaction ID, which points to an order. Now, when you fetch the order from the data table, the order would have a value of the transaction ID which it points to, right? So it's really not a version match. It's to check whether the entity itself exists as an attribute of the primary entity.
Yeah, but essentially, even that ID that you have embedded in that document has to be generated from somewhere.
I'm sorry?
The index ID you mentioned, right? The ID that you're embedding inside your document to create an MVCC kind of a thing?
Sure. So we don't read it from the document. To go more into specific implementation, we use columns in Hbase to figure out the column name happens to be the index, right? So we don't really need to get the entire value for a particular order key. We could just check whether this order key has a column which is the index value. So that's much efficient than unzipping and deserializing the entire order value to figure out whether the index was in the order entity.
Yeah, and also the other thing that you mentioned about in the first slide, you mentioned that you went for CP, that is consistency and partitioning, instead of a CA. Instead of a PA, partitioning and availability. So is it a business choice or is it a technical choice?
These are technical terms. If you're familiar with
CAP
theorem, you're talking about the first slide, right?
Yes, because it is more, a person not able to shop is a worse experience than a person adding duplicate items to a cart.
Okay. But this is, okay, then let me just help understand you better. We're not talking about systems here which are involved in search or involved in product page experience.
No, I'm just talking about the shopping cart.
Correct.
So it's like, it's more essential to have the shopping cart always up so that we are in control of our shopping destiny instead of it adding duplicate items to the shopping cart.
Well, that's a point, but I would leave it more from the product. There are different points of views here, right? So from the product point of view, one of the ways they think about it is it's better that we are always consistent, because when you're buying a bunch of things, right, there are offers that are applied. And it turns out suddenly one item is inconsistently shown. Now the entire offer that was applied is lost. And this is actually a, kind of a perception to a customer of mistrust. That, hold on, I did something and you're showing something else. So he loses faith on the platform, right? Again, this is more of a product philosophy on whether you want this to be consistent or not. I'm just giving you another school of thought of what's been gone into and why we have it as a CP store.
Hi. Did you try coprocessors for change propagation?
So coprocessors, yes. So coprocessors are a feature in Hbase, right? They are like hooks when things happen. But the problem with them is that they don't really play a major role when you have things like your entire region server crashing. So when your region server crashes, you need to start from where you left off, right? To make sure you don't have any loss in your change propagation. So more than coprocessor, it's much better to hook on to the replication stream that's happening, because replication has literally solved for the same problem. So we did look at coprocessors. In fact, the first thing we did was we were looking at ASOF, which was one of our own open source, but that was on 0.94 Hbase. And we realized that 1.2.4 provided more extensibility to plug this out of the box. So, and it turns out to be solving a lot of problems when you just listen to replication stream.
But then there will be some time lag between when you do the change propagation and when the actual write happened, right?
Absolutely. So it is an earthing process that is tailing your val file. So yes, there will be a time lag. But again, all of this is instrumented and measurable. So we can always set bounds to what would be the time lag, right? And you get to control the number of consumers, which is chunking out this data and pushing it to Kafka. So largely we do micro batching, which is way more efficient in meeting our scale requirements. In fact, currently, I don't think we've faced any issues or lags in this particular push in production.
How did you manage the transition from older data stores to Hbase at Flipkart scale, number one, and two, a lot of consumers hitting the older data stores?
Okay. I got the first question. How did we manage this transition at Flipkart scale? What was the second?
No. The point is at Flipkart scale,
right,
there's so much data
right,
sitting in the older data stores.
Right.
Now we are moving to a brand new world.
Correct.
On Hbase.
Correct.
Right? And there are a lot of consumers who are hitting the previous data stores.
Okay.
And they need to migrate to Hbase now.
Sure. So let me answer that question. So one thing is, let me start with the last part, a lot of consumers hitting that data store. So with the service-oriented architecture approach we have at Flipkart, we ensure that a data store, which is for a particular service, is not accessed by any other service other than this particular service. So in other words, if I want to now change this data store, it's very simple, and it's only for, like, the store used by checkout was not being accessed by anybody other than checkout. So that was one of the principles with which these services were. So we didn't have the problem of any other service hitting this data store. We were bounded by just making sure the app talking to Redis now has to move to, let's say, Hbase, right? We called it Yak internally because of all the customization. And in terms of the volume of data, the only major challenge we had was with order management system. In fact, payments we are still in process. Because order management is the system which had large amounts of data, around 2 terabytes, and the life of the data is around 3 years. But the other systems like checkout cart, the life of the data, checkout is a session object, right, is usually just 30 days. And that 30 days is for debugging when customer complains that I tried something and I couldn't check out the product. Cart again is, account card is longer, but we have another version called version card, which is again for the checkout session. So largely stores which were transient with a lesser TTL, we didn't need to migrate. We just needed to do AB and do a consistent hash movement of data from here to here, and then cut off this database on a long run. For systems like order management, it was a bigger challenge. We had to migrate a lot of data, and then again we had to go with an AB strategy to say that, let's say, order IDs which fall into this bucket, start going into this store from the creation, right? So new orders created from this bucket will only be on this data store and not. And on a long run, we took a small downtime to take the small differentials and move it out. So that's one way we went about migrating.
Hi. I'm curious to know how do you decide when to isolate tenants and when to keep them co-located? Because
we always isolate our tenants.
You always isolate. Okay, so that's
you need to know what is the performance you can get per tenant.
Right.
And
right.
the minute you co-locate, it's gone. We co-locate. We have a miscellaneous tenant bucket, which is for all experiments. So where performance doesn't matter.
Right. Okay. So that makes the things easier.
Yeah.
Okay. Thank you.
So with this Hbase cluster, when you talked about replication, it was replication within the data center or across data centers?
Across data centers.
Okay.
So again, I was talking about replication as something we use for change propagation. The consumers of change propagation do not necessarily need to be on a different data center. In our case, in order management system, we do have a consumer which is across data center for our hot standby. But we could have consumers within the same data center which are triggering fulfillment. So every order creation has an event trigger which results in a fulfillment call, and that's through this change propagation.
So do you usually use the DR data center sometimes? I mean, or it's just?
So it's an active hot standby setup. We haven't had the need to switch data centers till now. We've done that once when we moved to a different cloud setup. We have a private cloud at our end, but we haven't had an instance of getting the hot standby promoted as master. That is something we are working towards, as part of BCP DR and doing a drill run. But yeah, as of now we haven't had, but we have a hot standby just in case.
Hi, I saw a lot of compaction happening in the system. So when you compact the data, do you again go and do any updates to the data?
So the compaction
do you do updates to the compacted data?
So let me put it this way, right? So updates would keep coming based on the system interactions. Like, to give you an example, for an order management system on its life cycle journey, we would be listening to fulfillment events and updating the nature or state of the order, right, in its life cycle. Compaction, again, is more systemic, which is at a frequency of how many files that have been generated to compact them together. So in a sense, we don't really correlate the frequency of updation to the frequency of compaction in this case. Where we do correlate is, we know, for example, systems like checkout, where updates will happen within the 15-minute window. So largely, if you can size your memstore big enough, all these updates will happen on the in-memory memstore file. And when it gets flushed, you're not going to have multiple files having the same checkout ID. So that is one advantage when you have a lot of hot reads and you don't have stale reads. In terms of us tuning for compaction, the way we go about that is largely, like I mentioned earlier, we're saturated on disk. And compaction is a lot of read and write to disk. So we try to throttle the compaction to ensure that we don't saturate on disk and ensure that it doesn't affect read performance, right? We don't have too many files. So it's a balancing act that we play between the compaction periodicity and the memstore size to scale for read and write access patterns.
It's mostly the older data that you are keeping, you just compact it and keep it there, right?
Correct, but to answer in terms of older data, we actually even tire it. We have only 6 months data, and all of the systems I've talked about are on SSDs, right? Yeah. Except for OMS, which has got older than 6 months data sitting on disks.
Do you monitor anything on SSD wear out counts?
Do you monitor, sorry, can I get a question?
On machine SSD, you said it is mostly SSD machines, right?
Correct.
Do you have any mechanism to check the wear counts of SSDs and then how frequently it is getting deteriorated?
Yes.
With all these read writes happening.
Yes, so the last slide which I had shown you is about we monitor basically a lot of metrics on our VMs. These are all VMs, right? We do monitor the write and read QPS out of these SSDs based on the chunk that's been given to us from the VM, correct? And largely we have alerts when we know we are saturating our disks. And we do have monitors to know what's saturating it. Is it compaction that's running, or is it actually the write which is hitting the val file? So those are the aspects we look at, yes. And if we determine that we are unable to do anything about it, we add more boxes.
Sure. Thank you, Gokul.